All right, so we are continuing chapter 12, and this is the part of the chapter where things get exciting. We start talking about how impulses are going to actually travel throughout our body, thanks to membrane potentials. And this meme will make sense, hopefully, after this lecture is done. So let's just review and talk about some of the parts of our neuron. So remember, we have our axon, which is, actually, let me get my little drawing tools. We've got the axon here, which is that single long cytoplasmic process, which can be quite long, up to 1 meter in length. And that is the part of the neuron which is going to propagate the electrical signal, which is our action potentials. At the beginning of the axon, we have what's called the initial segment. Basically, it's just the base of the axon. Coming off our cell body, we have what's called the axon hillock, which is basically just the region where that initial segment is going to attach to the cell body. And then where that axon hillock meets the initial segment is called our trigger zone. And the trigger zone will be important when we talk about action potentials. The axoplasm is the cytoplasm within the axon. Remember, we've got to have a special name for everything in anatomy. So cytoplasm within the axon is axoplasm. Similarly, the plasma membrane of the axon is the axolemma. Collaterals were those branches of the axon that can come off. There's none on this picture, but if we had one, we would have little branches coming off the axon, making their own telodendria. And then the telodendria is basically the extension of the distal axon where it branches off. Sometimes it's called the terminal branches. And then at the end of the telodendria branches, these little tips are called our axon terminals, our synaptic terminals, or synaptic bulbs. And that's where the communication with another cell is going to occur. So we would have another cell, possibly another neuron or a muscle cell here. And this region here, this tip of the telodendria, that synaptic terminal, is going to communicate with the cell next to it. And that's what's called our synapse. So that synapse that we just mentioned is a specialized site where that neuron communicates with another cell. It could be another neuron, it could be a muscle cell, it could be a gland, etc. And some terminology at the synapse, we have the presynaptic neuron, which is going to be the neuron that's sending the message. So that message is going to travel down that axon to the synapse. And then this postsynaptic neuron is going to be the neuron receiving the message. And we have two different types of synapses. We have electrical and chemical synapses. And we'll talk more about synapses in the next lecture. So how do our neurons actually create impulses to send that information across that synapse? How do we get that message to travel down the neuron? Well, our plasma membranes of our neuron produce electrical signals thanks to the movement of ions across the membrane. There are several different membrane processes involved in this. So let's talk about some of the terminology. The first process we're going to talk about is the idea of resting membrane potential. Remember, in our first unit, we briefly discussed that our cell membranes have a resting membrane potential, where the extracellular and intracellular fluids have a different charge. And because opposite charges are attracted to each other, it creates this potential energy, meaning these charges want to come together, but we have that barrier of the cell membrane between them, so they have the potential to move together. They have work that they could do if we remove that barrier. We also gave the analogy of a dam holding back water. That water that's held back by the dam is that potential energy. If we remove the dam, the energy will be released. Or you can think about positive and negative ends of a magnet. If you held a positive and a negative end of a magnet slightly apart, they have the potential energy to join together because, like the ions, the opposite charges are attracted together. Inside our cells, we see an overall negative charge. Inside the cell, we have both positive potassium ions, but we also have these large organic anions, which have a negative charge. So inside the cell, we see lots of potassium, but we also have these large anions, which have a big negative charge. So overall, inside the cell, we have a negative charge. Outside the cell, we have an overall positive charge. Outside the cell, we find lots of positive sodium ions and also some negative chloride ions. But overall, we've got that positive charge thanks to those sodium ions. So overall, inside, the charge is negative, outside the charge is positive. And I kind of remember this by looking at the letters within the cell. We've got an N in inside and an N in negative, an O in outside, and then O in positive. So overall, negative inside, positive outside. If we stuck a probe actually into the membrane to measure that potential in millivolts, the actual resting membrane potential overall has a negative charge. So that resting membrane potential provides the potential energy for several other membrane processes to occur, which are all part of the transmission of an impulse or signal. First, we have a graded potential, which is a temporary localized change in the resting membrane potential caused by a stimulus. And we often see that in the dendrites or cell body. So a stimulus such as a chemical binding a channel and opening it causes a localized change in resting potential. Then we have what's called an action potential. And an action potential is an electrical impulse that's produced thanks to that graded potential. And the action potential propagates along the surface of the axon to our synapse. Then we're going to have our synaptic activity here at the synapse. What's going to happen is that axon terminal is going to release a neurotransmitter, a chemical, and that neurotransmitter is going to bind to the second cell, the postsynaptic cell, and that's going to produce a graded potential in that postsynaptic cell membrane. And then we're going to have information processing. So the response of that postsynaptic cell to that neurotransmitter is going to be what is our information processing. So it's basically deciding what the cell, or telling the cell what it needs to do in response to that stimulus. And just once again, looking at where this is happening, resting membrane potential. Initially, we're going to have resting membrane potential all across our membranes. When our cell is resting, no processes are going on, we are going to have a resting membrane potential. That graded potential is going to be that localized change in membrane potential as a result of a stimulus, and that usually happens at the dendrites or the cell body. Then that action potential is going to take place, travel down the axon to the synapse. Then we have synaptic activity taking place, where that synaptic bulb is going to release a neurotransmitter and communicate with our postsynaptic cell, who is then going to perform information processing, deciding what needs to be done in response to that message. Then that postsynaptic cell might end up getting a graded potential as a result of that synaptic activity, which then may trigger an action potential, which then may trigger synaptic activity in that cell. So more about resting membrane potential. The fluid inside and outside of our cell differ in ionic composition. We mentioned this before. In the extracellular fluid outside our cell, we have a higher concentration of those positive charged sodium ions and negative charged chloride ions. And then inside the cytosol, we have a high concentration of positive charged potassium ions, and then lots of those negative charged proteins, also called organic anions. So overall, we end up with that net negative charge inside and net positive charge outside the cell. The cell membrane is selectively permeable. Remember, we talked about cell membranes before. Selectively permeable means it lets some things cross and not others. It contains membrane channels. Remember, we talked about membrane channels before. And those membrane channels allow the ions to leave or enter the cell. And the permeability is going to vary depending on the ion. And we have passive processes acting across the membrane, such as diffusion, that involve both chemical and electrical gradients. When we say chemical gradients, that's what we thought of before as concentration gradients. So the ions are trying to move from an area of lower concentration to an area of higher, from an area of higher concentration to an area of lower concentration via diffusion. So because we have more potassium inside the cell, it's going to be driven out of the cell. And sodium, conversely, we have more sodium outside the cell, so it's going to be driven inside the cell thanks to that concentration gradient. The membrane is more permeable to potassium, so more potassium is able to leave than sodium is able to enter. And these ions are entering or leaving via passive leak channels in the membrane. We have more of these potassium leak channels than sodium leak channels, and that's why the membrane is more permeable to potassium. So that's our chemical gradient. We also have an electrical gradient, and that gradient is created because we have those positive and negative charges separated by the membrane, and those opposite charges want to move towards each other. And the electrical gradient can either reinforce or oppose the chemical gradient for each ion. So the chemical gradient may be wanting to move potassium out of the cell, and the electrical gradient may be wanting to move potassium in or out. So depending on the ion, the electrical gradient may be the same as the chemical gradient in terms of which way the ion's moving, or it may be opposite. When we add these two forces together, the electrical and the chemical gradient, we get the electrochemical gradient. And the electrochemical gradient overall is going to determine where that ion is moving. So let's talk about those passive processes again. The ions, sodium and potassium, can move due to those passive processes of chemical or concentration gradient and electrical gradient. Opposite charged ions are going to attract towards each other and try to eliminate that potential difference. And then the ions are also going to move towards the area of lower concentration. So that's our chemical gradient. So the sum of these two forces, the sum of the electrical gradient, the ions wanting to move or being attracted towards the area of opposite charge, and then the chemical forces, moving that concentration gradient toward an area of lower concentration. When we add those two forces together, then we end up with the electrochemical gradient. So when we're at resting membrane potential, the cell is not doing anything, just hanging out, chilling. The net electrochemical gradient for sodium is such that sodium is driven into the cell. The net electrochemical gradient for potassium is such that potassium is going to move out of the cell. And if you are more interested in this, more details in this process, your book does go into it in detail, but it's not something that you need to know, and it takes a lot of time to explain. So the main idea that I want you to have from this is that we add those electrical and chemical forces together to get the electrochemical gradient, and sodium's electrochemical gradient is driving it in, potassium is moving it out. Unfortunately, my face is blocking this mnemonic, but one mnemonic people sometimes use is Nike, meaning sodium in, potassium exits. I also sometimes think of the sodium gets sucked in, SNS, potassium K gets kicked out, or the other one I sometimes use is that we're shaking in our salt, so we shake in our sodium and we throw out our bananas. We throw out our potassium. So shake in your salt, shake in your sodium, throw out your bananas, kick the potassium out of the cell. And remember, overall I said that the resting membrane potential, if we stuck a probe into the cell membrane and measured in millivolts, it would be -70 millivolts. So in addition to the passive processes of the electrochemical forces, we also have active processes to maintain our resting membrane potential. The cell wants to maintain that potential difference so that when it needs to use that potential energy, it can. So we want to maintain that resting membrane potential when the cell is not actively performing something. So the active process, one of the active processes that helps maintain this, is the sodium-potassium exchange pump. We mentioned it earlier in the semester when we were talking about cell membranes, and this is a pump that's powered by ATP. It's an active process, so it needs energy. It needs ATP. This pump is going to eject 3 sodium out of the cell for every 2 potassium it brings in. So it's basically balancing out the passive forces of diffusion and reversing that Nike, that sodium coming in, potassium exiting. And this is going to help stabilize our resting membrane potential and keep it at -70 millivolts. And one of the ways that I remember which ion we're moving more of is I use this, I like more salt than pepper. So we have more sodium or salt coming in than our pepper, our potassium. So we have, remember, when we have those passive electrochemical forces, normally diffusion is going to want to make our sodium enter the cell, right? Those passive forces are going to push sodium into the cell and push potassium out of the cell. If that keeps happening and nothing changes it, then we lose that resting membrane potential. We want to maintain that, so this sodium-potassium pump is then going to reverse what just happened passively, and it's going to kick some of those sodium out and bring some of those potassium back in. And it's going to kick out 3 sodium and bring in 2 potassium. So more salt than pepper. Some more terminology related to our electrical gradient. Remember, oppositely charged ions will attract towards each other and try to eliminate that potential difference. When those charges move, in order to eliminate that difference, that's what we call a current. If a barrier, like a cell membrane, separates the oppositely charged ions, the amount of current is going to depend on how permeable that membrane is to the ions. If we have a more restrictive membrane, a less permeable membrane, we're going to have a higher resistance. And if we have a higher resistance, the current is going to be small. Conversely, if we have a low resistance, the current of ion movement is large, and the ions can flood across the membrane. So the passive or leak channels that we have for sodium and potassium that we discussed in previous slides are important in establishing that normal resting membrane potential, and those channels are always open, but their permeability is going to vary in response to local conditions. But we also have active or gated channels, which are going to open and close in response to stimuli, and these are usually closed at resting membrane potential. And we have 3 different classes of gated channels. we have chemically or ligand gated, voltage gated, and mechanically gated. Our chemically gated or ligand gated channels, which you can see in this image, these open or close when they bind a specific chemical or ligand, such as acetylcholine, which we find at a neuromuscular junction where a neuron communicates with a muscle cell. And these are the found most abundantly in the dendrites and cell bodies of our neuron, where our synaptic communication is going to occur. So with these channels, the channel is normally closed and it has a special site for binding a ligand or chemical. That chemical binds that site, it causes the channel to open, and then ions can flow through. Then we have our voltage-gated channels. These channels are going to open or close in response to changes in the membrane potential. And we find these in areas with excitable cell membranes. Excitable meaning that those membranes can generate and propagate action potentials. For example, the axons of unipolar and multipolar neurons, and the sarcolemma, or cell membrane, of skeletal and cardiac muscle cells. In this chapter, we are most concerned with voltage-gated sodium, potassium, and calcium ion channels. What happens when the membrane potential changes, these sorry about that little interruption. So I apologize if I repeat myself here as I come back. So those voltage-gated ion channels are going to open or in response to a change in the resting membrane potential. So here's our little probe monitoring our resting membrane potential. So if a current comes along, and thanks to ions flowing into or out of the cell next to this gate, and that current changes our resting membrane potential. So you can see here it was -70, it's going now to -60 thanks to a current. That change in the potential is going to trigger this channel to open, and then our ions can flow in. Some of these channels have multiple gates. Our voltage-gated sodium channels have what's called an activation gate and an inactivation gate, and they, depending on the situation, they can be open, both gates open, or the inactivation gate closed so that nothing can flow through. So I'm not going to quiz you on those situations, just know that there are gated channels with multiple gates. And then our third kind of gated channel is our mechanically gated ion channel. And these mechanically gated channels are going to open in response to physical distortion, such as pressure that's being applied to the membrane. So an example of where we would see this would be when we are having the sensation of touch. Somebody pushes on our skin, on our hand, and that touch actually is going to distort that cell membrane, and that distortion of the membrane as pressure is applied then opens that mechanically gated channels and the ions can flow through. So in this unit, we are mainly going to be discussing the chemically gated and voltage gated channels. Those are the channels that are involved in our transmission of impulses down a neuron. So where do we find these channels on the neuron? In our neurons, the chemically gated ion channels, or ligand gated, you can call them either, these are located on the cell body and dendrites. So remember, our cell body, our dendrites. So this is where you're going to find those chemically or ligand gated channels, which makes sense if you think about it, because if the cell is receiving a signal from another neuron, that neuron is going to communicate with this end. So it's going to release something like a neurotransmitter, which is then going to bind to that chemically gated channel on the postsynaptic cell, and then that's going to trigger opening of the channel. Our voltage gated channels are going to be found on the axon and also on the telodendria at the axon terminal. So all along the axon, we find our sodium and potassium voltage-gated channels. At the axon terminal, we're going to find voltage-gated calcium ion channels. And we'll talk more about those voltage-gated calcium ion channels in the next lecture. So the distribution of these channels affects the way the neurons function. At resting membrane potential, remember most of these gated channels are closed. Once the channels open, the rate of ion movement across the membrane increases, and that changes our membrane potential. So any stimulus that opens one of these gated channels can produce what's called a graded potential. And a graded potential is a change in that membrane potential, a change in resting membrane potential that can't spread far from the stimulus. The degree of depolarization, we say depolarization, that means changing the membrane potential to a less negative number. So, for example, if we went from a negative 60 to a negative 50, so that change to a less negative number decreases the further away we get from the stimulus, meaning that local current that's been created is dissipating. So remember, we have, I'm going to try and do a little drawing here. So we've got a channel here across our membrane, and we've got our sodium out here. We've got our potassium inside. Should be that. Our potassium inside. And this, say, is a chemically or ligand gated channel. Our ligand comes in and binds, and that is going to allow our ions to flow. Sodium is going to flow in initially, and that sodium flowing in, remember it has a positive charge, is going to create a local current along the membrane of positive charges as that sodium flows in. And so that's going to change the membrane potential here to a more positive number, and that's called our depolarization. But as we move further away from the stimulus, from this gate that's opened, that degree of change, that degree in potential is going to decrease because that local current is going to be dissipating. An example of this is, as I just drew, I guess I should have waited to draw that, is our chemically gated sodium ion channels on the cell membrane. So, sorry about that. Trying to record lectures at home with children can be a little challenging, but I'm trying to get this done so you guys can listen to it this week. So, our chemically gated sodium channels that are found on those dendrites, they bind a ligand, the channel opens, and then those positive sodium ions enter and move parallel to the plasma membrane as I just drew. That creates a local current, which creates a depolarization. So that depolarization, remember, is a shift towards a less negative potential in the plasma membrane next to the channel. And that is our graded potential, that change to a different membrane potential locally at that membrane right around where the stimulus occurred. And with these graded potentials, that degree of change in this example with the sodium channel opening, it's a depolarization, is going to decrease as we move away from the stimulus. And that change in membrane potential is going to be proportional to the stimulus. So a larger change in potential is going to occur in response to a larger stimulus. A smaller change in potential is going to occur in response to a smaller stimulus. Kind of the way that I think of this is if we had Our graded potential would be this person shouting here. If you're standing close to them, it's going to sound really loud. So that that depolarization is going to be large. As we move further and further away from them, it's going to get smaller and smaller. So as we move further away from the stimulus, that change is going to decrease. Another image that I kind of think of with a graded potential would be dropping rock into a pond and looking at the rings of water after you drop the rock in. As you move further and further away, the magnitude of those little waves that are created are going to decrease. But if we drop a giant boulder in, it's going to create larger waves than if we put in a tiny pebble. But eventually, as we get away from that rock, those waves are going to decrease. So that's a graded potential. So this image is taken from your textbook, just to kind of give you an idea of what is happening when some of these chemically gated channels bind and how we get a graded potential. So in our resting cell here, our membrane potential is negative 70 millivolts. Our gates are closed, and we've got positive sodium and negatively charged anions on the inside. So we have a membrane potential. Those positive and negative charges want to move towards each other. We get a stimulation, which is the binding of a ligand or chemical to that chemical or ligand gated channel, and that's going to cause the channel to open. That opening of the channel is going to allow positive sodium ions to flow into the cell. And those positive sodium ions flowing into the cell is going to change the membrane potential of the cell. Because we have positive ions coming in, it's going to make the membrane potential more positive. So we're going from negative 70 to negative 65. With our graded potential, the spread of those sodium ions along the plasma membrane is going to produce that local current, which is causing that depolarization, so going to a less negative membrane potential. But as we move further and further away from the initial stimulus, that change in potential is going to decrease. So the further we get from the stimulus, the less of a change we're going to see with a graded potential. So after our depolarization, remember depolarization happened when we had those, whoops, where's my pen? Here's our gate. So we had those positive sodium ions flowing in, brought more positive charges along the membrane. It made the membrane potential was less negative. So after that polarization, if we remove the stimulus that caused this channel to open and we close these channels, the membrane potential is going to return to normal. It's going to go back to its original value, and that's called repolarization. And that repolarization is usually going to involve a combination of ion movements via membrane channels and ion pumps like that sodium-potassium pump. Remember that sodium-potassium pump, that is a active process that reverses that sodium and potassium out. If, however, instead of having a sodium channel open, we have a potassium ion channel open in response to a stimulus, we get the opposite effect. Instead of depolarization, we get hyperpolarization. The rate of the potassium ions flowing out of the cell increases, and then the inside of the cell, as the potassium flows out, is becoming more negative because, I'll draw a little picture again here. So here's so this is going to be a potassium channel. We get a ligand bind, our potassium channel, and all these positive potassium ions that are inside are going to be driven out. Because remember, potassium exits. We throw out our bananas. So all these positive charges that were inside up against that plasma membrane are going to be lost as they flow out of the cell. And so that loss of those positive ions is going to increase the negativity of that resting membrane potential. And that's called hyperpolarization. Once that stimulus is removed, so if we get rid of this little ligand, this gate closes back up, then our membrane will repolarize, such as using the sodium-potassium pump to reverse that exiting of potassium, bring the potassium back in, and that will repolarize the cell membrane and return it to its resting membrane potential. And this is an image taken from your book, just to give you more of a visualization of depolarization versus hyperpolarization. So on the left-hand side here, here's our resting membrane potential, negative 70 millivolts. When our cell is at rest, it's at negative 70 millivolts. If we have a sodium channel open, sodium is going to be driven in. Remember, shake in your salt. And that sodium coming in is going to make our membrane potential become less negative. So if we look at our measurements on the side, that sodium is going to come in, and our millivolts is going to go to negative 60, which is less negative. That's a depolarization. If we then remove whatever stimulus opened that sodium channel, the sodium channel is going to close, and then our membrane is going to repolarize thanks to the sodium-potassium pump and get back to negative 70 millivolts. Conversely, if we had a potassium channel open, we start out once again at negative 70 millivolts. Potassium channel binds a ligand and opens. Potassium flows out, kick out your bananas. The potassium flows out of the cell. The cell is losing that positive charge, which means that membrane potential is going to get more negative. So you can see here our membrane potential is decreasing to negative 80 millivolts. If we remove that ligand and close that potassium channel, then our sodium-potassium pump can start working to return to our resting membrane potential, which is negative 70 millivolts. So, to sum it up, we're normally at negative 70. If a sodium channel is opened, we get a depolarization. We move to a less negative charge. If we close that channel, we get a repolarization. Go back to negative 70. If it's a potassium channel that's opened, potassium exits, we kick out our bananas, we get a hyperpolarization. We're getting to a more negative charge. If we remove whatever that stimulus was, close that potassium channel, we're going to repolarize to our normal resting membrane potential of negative 70. All right, so now for the exciting part, action potentials. So how that message is going to travel down the axon. So I would pause here for a moment and watch this video, which is a little kind of cartoon about how action potentials travel down the axon. So take a moment and watch that, and then come back and we'll talk about it. So these action potentials, which are basically that impulse traveling down the axon of the neuron, are changes in membrane potential, changes in that resting membrane potential. Once initiated, once that action potential is triggered, it affects the entire excitable membrane versus our graded potential, which only affected the membrane locally. So remember, the graded potential was triggered by a stimulus and it caused a localized change in membrane potential. The further away we got from that stimulus, the less significant the effect on the change in potential. So it had just a local effect. With the action potential, once we reach that threshold to start the action potential, the entire excitable membrane is going to be affected. So this action potential begins at that initial segment of the axon, the very beginning, right next to the cell body, and it's going to propagate or travel all the way down to the axon terminal at the end of the neuron. And this potential, this action potential, does not diminish as it moves away from the source. Remember, the graded potential, the further we got from the source, the less significant the effects on the membrane. So as we moved away from that source, the graded potential decreased. An action potential is stimulated by a graded potential that causes a large enough depolarization to bring the axolemma, remember the axolemma is the plasma membrane of the axon, to a threshold level at the trigger zone. If you remember, the trigger zone is basically where that axon hillock met the initial segment of the axon. So let me draw a little picture here of our, so here is our cell body. This is a very simplified neuron. So we had our cell body, there's our axon and our axon terminal, and the initial segment of the axon is the beginning of it. The axon hillock is kind of the part of the cell body that meets the axon, and that spot where those two meet is that trigger zone. So if we get a large enough depolarization to bring that axolemma to what we call threshold at that trigger zone, then we initiate an action potential. The threshold for an axon is from between -60 and -55 millivolts. So remember, on average, our resting membrane potential is -70 millivolts. Remember, a depolarization means making that membrane less negative. So we're going from a -70 millivolts to a -60 millivolts to generate that action potential. So that's a depolarization because we're getting less negative, we're getting closer to zero. So if we can bring that membrane to the threshold level, if that graded depolarization, that initial stimulus and depolarization from that graded potential can get us to that threshold level, then the action potential is triggered. The action potential has to be generated at one site before it can be propagated away from that site. So we've got to get that action potential triggered at that trigger zone for the action potential to then travel all the way down. Once that action potential is triggered at the trigger zone, once we reach threshold at the trigger zone, once we've depolarized to -60 millivolts at that trigger zone, then because this is an excitable membrane, the action potential will travel all the way to the end. Okay, it's going to affect the entire membrane versus that graded potential, which is only going to act locally. So action potentials have what's called an all or none or threshold principle. So we said we needed that graded potential to depolarize the axolemma, the plasma membrane of the axon, to that specific level that'll trigger the action potential. So when we say threshold, as I mentioned before, that's the membrane potential at which the action potential is triggered or generated. In most of our neurons, between -60 and -55 millivolts. So the membrane usually has to depolarize 10 to 15 millivolts from that resting membrane potential to trigger the action potential. if we have a graded potential and the depolarization from that graded potential is not large enough to reach that threshold, so say we had a ligand bind a chemically gated channel on a dendrite, and it caused a graded potential, a localized depolarization, but it only depolarized, say, 5 millivolts, and we only got to 65, we would not be able to generate an action potential and nothing would happen. So only if we can reach that threshold will that action potential be generated. So we're going to have a large enough depolarization to reach that threshold level. Local currents from that graded depolarization of the axon hillock cause depolarization of the initial segment of the axon. So that graded potential, draw my little picture again. So here is our trigger zone. We'll say this is our axon hillock, and this is our initial segment. And we have a channel here that can bind a ligand. So ligand binds that chemically gated channel, opens the channel. If this is a sodium channel, the sodium is going to flow in, and that's going to cause a graded depolarization. If that graded depolarization is large enough when it reaches the axon hillock and then the initial segment at that trigger zone, then the action potential is triggered. And the trigger zone, once that action potential is generated at the trigger zone, that action potential is going to propagate all the way down to our axon terminal. Oh, it's like a tongue twister today, sorry. If that depolarization, I said, is not large enough, if that graded depolarization from that initial stimulus on the dendrite or cell body is not large enough to depolarize to threshold, then no action potential will be generated at the trigger zone. So we will not get any action potential traveling down the axon. So it's an all or none response. Either the action potential is triggered and it travels all the way down the neuron, or it's not triggered and it doesn't travel. It's not like the graded potential where if it's a big stimulus, it'll travel a little ways down and stop, or if it's a big stimulus, it'll travel all the way to the end. It's an all or none. So if we can reach threshold at this trigger zone, it's going to go all the way to the end. Same speed all the way to the end. Your book gives an example that relates to this idea of all or none, which is the firing of a gun. So I'm not super familiar with guns, but anybody probably can understand this concept that to fire a gun, your finger has to apply pressure to the trigger, right? If enough pressure is applied to the trigger, then that bullet is going to be fired. And it doesn't matter if you pull the trigger just enough to fire the gun, or if you pull it super hard, that bullet's going to be fired either way, and it's going to go at the same speed. It's not like if you pull the trigger extra hard, the bullet's going to go faster. But if you do not pull the trigger hard enough to reach that threshold, no bullet is going to leave the chamber. So that's kind of how the action potential works. If you pull the trigger tight, and if you pull the trigger to the threshold, so if we depolarize at that trigger zone to threshold, that bullet or action potential is going to fire all the way to the end. Same speed, it's going to go. If we don't reach that threshold, if we don't pull that trigger on the gun hard enough to reach that threshold, or don't depolarize that trigger zone to threshold, then no bullet's going to be fired, no action potential is going to travel down the axon. So what steps are involved in this generation of an action potential and what's happening to the membrane potential throughout this process. The image here is taken from your textbook, and it shows us the membrane of the it shows us the measurement of the membrane potential in millivolts throughout the course of an action potential. So before we begin our action potential, we are at resting membrane potential, or negative 70 millivolts. So that's right here. So remember, resting membrane potential about negative 70 millivolts. And at this point, our axon and its terminals are full of voltage-gated sodium ion channels that are closed. So at resting membrane potential, within the axon, we've got all those voltage-gated channels that are closed. Remember, voltage-gated channels open and close in response to changes in the membrane potential. That's why they're called voltage-gated, because that change in voltage is going to open them, versus the chemically or ligand-gated, which are going to open in response to binding a chemical or ligand. So all those gates are closed. At step 1 here, we get that graded depolarization. So that graded depolarization is going to be a result of that chemically gated sodium channel binding a ligand and opening, allowing positive sodium to flow into the cell. It's going to cause a graded potential. It's going to cause a graded depolarization because we have positive sodium ions flowing into the cell. It's going to make our membrane potential less negative. We're going to move closer to 0. And you can see that as that graded potential starts, our membrane potential is rising. And that's a result of those sodium ions flowing in. So if enough of those sodium ions flow in, if that graded depolarization is large enough to get us to this threshold level around negative 60 millivolts at the trigger zone, then opening of channels occur on that axon at the trigger zone. So we get to threshold because of that graded depolarization, and we've got then voltage-gated channels on the axon. Those voltage-gated channels are going to open, and the sodium channels are going to open first. So our voltage-gated sodium channels are going to open, and sodium ions are going to move into the cell. And that's what's happening here at step 2. And that causes a rapid depolarization. So all those voltage-gated sodium channels start to open at the beginning of the axon, and then sodium is going to flow into our cell. Remember, we shake in our salt. Sodium is going to flow into the cell. Sodium is positive, so it's going to cause this rapid depolarization of the membrane potential. The membrane potential was, say, negative 60 at threshold. Those voltage gates open, lots of positive sodium flows in, and we're going to get even more of a depolarization. We're going to get an even less negative value. So after those voltage-gated sodium channels open, those sodium ion channels are going to close. And as that, so sorry about that, those sodium channels open up, we get that massive depolarization from the influx of sodium into the cell. Once we get a depolarization to about the level of 30 millivolts, which we can see here at number 3, those sodium channels are going to close. They're inactive. Remember, those were the ones that had different gates. So that inactivation gate is going to close, and sodium is going to stop flowing into the cell. And at that point, our voltage-gated potassium channels are going to open. And remember, sodium flows in, we shake our salt in, potassium flows out, we throw out our bananas. So the potassium is then going to flow out of the cell. Remember, potassium is also positive. So now we have positive charges leaving the axon, crossing that axolemma, that cell membrane. And so those positive charges leaving the cell is going to lead then to a rapid repolarization. So we're lowering that membrane potential. We're going back to that -70. So that's a repolarization due to those potassium, those voltage-gated potassium channels opening. Then our voltage-gated sodium channels are going to stay inactivated. They're going to stay closed until we have repolarized to the threshold level. And at that point, they're going to return to their normal status of closed but able to open. So they are closed, but if we have a large enough stimulus, they could open back up. The voltage-gated potassium channels begin to close as we reach that resting membrane potential of -70 millivolts. But potassium ions are going to continue to leave our cell until all of those potassium gates have closed. And this produces a brief hyperpolarization, which you can see in step number 4, where the membrane potential becomes even more negative. So potassium is still leaking out of those channels, so we're still losing some of those positive charges. So we actually get a little bit below resting membrane potential, and that's called a hyperpolarization. And that hyperpolarization will eventually stop and will return to resting membrane potential once all of the voltage-gated potassium channels have closed. And that is the point that our action potential is over. Now, note that during stages 2 and 3, this is referred to as our absolute refractory period. It's this kind of red area here. Whoops. I'm just going to erase some of the stuff I have drawn on here so you can see better again. So our absolute refractory period, so in stages 2 and 3, and our absolute refractory period, that means all of our sodium channels are either open or inactivated. Therefore, sodium cannot flow across the membrane, which means that this membrane, this neuron, cannot respond to further stimulus. So even if we had a stimulus occur that started a graded potential, it's not going to result in another action potential coming down the axon at that point. And then we have stage 4, which is in our relative refractory period. And this begins when those sodium channels regain their resting condition where they're closed but able to be activated. And at this point, they can only respond to a larger than normal stimulus because the local current of sodium ions has to be large enough to counteract the exit of the positive potassium ions that are still exiting the cell. So at that point, at number 4, we could potentially start another action potential if we have a larger than normal stimulus. You can see here at point 4, we are more negative than our resting membrane potential, right? We're probably down at -80. So in order to reach threshold, we would need a larger than normal stimulus. Normally, say we would need about a change in 10 millivolts. During the relative refractory period, we might need -20 millivolts or 20 millivolts. So basically, for this, just know that there is a period of time that another action potential cannot be generated. And then we also reach a point at the end of the action potential where another action potential could be generated if we have a larger than normal stimulus. So during our action potential, remember, sodium is entering the cell, shaking our salt, potassium is exiting, kick out our bananas, and we can have many action potentials generated per second in some neurons. So they are rapidly generating to return our ions to that pre-stimulation level and restore resting membrane potential so we can have those other action potentials be generated, we can have those other impulses be generated, our membrane uses that sodium-potassium exchange pump. So remember, this is an active channel, meaning it requires ATP, requires energy, and it transports 2 potassium ions into the cell and transports 3 sodium ions out of the cell. So we're kind of reversing Nike, reversing that sodium and potassium exiting. So with the sodium-potassium exchange pump, we are kicking out the salt, kicking out sodium, bringing in the potassium. And this was the way I remember it's 3 sodium and only 2 potassium, as I like salt more than pepper. P for potassium. You can use whatever memory device you like, but that's how I remember which one is 3 and which one is 2. So this pump helps keep our ions concentrations at acceptable levels over prolonged periods of time. So we want that neuron to be able to continue to fire or generate action potentials, for it to continue to work. So for that to happen, we need the sodium-potassium exchange pump to restore that resting membrane potential so that we can continue to generate more action potentials. So in order to do that, we need energy. So if we don't have enough energy, we are not going to be able to generate action potentials. We are not going to be able to generate impulses down our neurons. So we have 2 different ways that we can move an action potential along an axon. And the movement of an action potential down an axon is called propagation. We have continuous propagation and saltatory propagation. Continuous propagation occurs in unmyelinated axons. Remember, we talked about myelin in the last lecture. We have myelinated and unmyelinated axons. So in our unmyelinated axons, it's called continuous propagation, and our myelinated, it's called saltatory propagation. So let's take a look at those 2 types. So continuous propagation, once again, is in those unmyelinated axons. And what happens here is the action potential affects one segment of the axon at a time. Each time a local current develops, it moves forward to the next segment along the axon, repeating until we get to the axon terminal. And this happens at a speed of about 1 meter per second. And the example I think your book might use of this is if you had a line of people standing, passing a message down to the end of the line by just turning and whispering the message to the person next to them. Then that person turns and whispers the message to the person next to them. Then that person turns and whispers the message next to them. And on and on and on until we get to the last person, or until we get to the axon terminal. So basically with continuous propagation, here's my very basic neuron. And there's no myelin here. So with continuous propagation, we get our action potential generated because we reach threshold at the trigger zone. And that axon, each little segment, the action potential is going to travel down. So it's that local current's going to, travel here, and then here, and then here, and then here. So it has to travel all the way down that membrane, all the way to the axon terminal for that message to reach the axon terminal and the synapse. So it's slower because those ions have to be flowing. Remember, sodium flowing in, potassium exiting, sodium flowing in, potassium exiting, sodium flowing in, potassium exiting, all the way down that entire membrane. So that's continuous propagation. So our saltatory propagation is going to occur in our myelinated axons. That myelin that covers the axon prevents continuous propagation. Our sodium and potassium ions can only easily cross the membrane at the nodes. Remember, when we have a myelinated axon, we've got these little myelinated areas, and then in between those myelinated areas, if you remember, those are called our nodes of Ranvier. And so those ions can only pass at those nodes. So depolarization is only occurring at those nodes. And what happens is that local current that's created from the ions crossing the channels is going to end up jumping from node to node. And this makes it faster than our continuous propagation was, where we had to travel down the entire length of the membrane. In this form, we basically get to skip across the internodes. And this is going to require less energy because we have less surface area involved, so less ion movement ends up being needed. And an example of this would be, say, if you had a group of people that were trying to get a message to the person at the end, and they had the people were spaced out across the room, and they had a megaphone, and so they were using the megaphone to shout to the person 10 feet away, and then that person could use the megaphone to shout to the person 10 feet away. So that method, that saltatory propagation, is going to be faster than the continuous propagation, where we've got to pass that message from one person to another, all sitting right next to each other. So in addition to myelination, other things can affect the speed of the action potential in one neuron versus another. So the diameter of the axon can affect propagation speed. The larger the diameter, the lower the resistance to the current, and so the faster the speed. And we have three different types or categories of axons, or remember, sometimes we call our axons our fibers, nerve fibers. We have three different kinds of axons with varying speeds depending on if they're myelinated and their size. So we have type A fibers. These are the largest and myelinated axons, so they're the fastest. Remember, myelinated means saltatory propagation. It's faster, it's jumping node to node. These are also larger in diameter, so they have less resistance. So we're going to go really fast here, up to 120 meters per second. So you can think of this as the text messaging of your neurons. And type A fibers are going to carry sensory information and motor neuron information that controls our skeletal muscle. And this type of fiber is used for critical information, such as motor commands to prevent injury. So say you burned your hand, touched a hot stove, and you would need to jerk your hand back very quickly to prevent injury. So that sensory information coming into your brain via the afferent branch of the peripheral nervous system, what needs to reach your brain quickly, and then that efferent branch, those motor neurons leaving your central nervous system to tell your skeletal muscle to contract so you can pull your hand away, needs to be fast too, because we don't want to leave our hand on that stovetop causing injury. So we need fast information. We need fast transmission of that type of information. So that's going to be type A fibers. Type B fibers are also myelinated, but they are a smaller diameter, so they have a little more resistance, so they're not quite as fast as the type A. These travel about 18 meters per second, so they're considered the email type of neuron. And then we have type C fibers, which are unmyelinated, so they're going to have to go through continuous propagation, which makes them slower, about 1 meter per second. So this is the snail mail version of information transmission. Fibers B and C are going to carry information from to and from the central nervous system on things like temperature, our general touch, pressure, and they're also going to be used to carry instructions to things like smooth muscle, cardiac muscle, and glands. So why don't we just have all type A fibers? Wouldn't it be nice to just get everything, all that information transmitted as quickly as possible? Well, the type A fibers are larger, and if we had all of our axons as type A fibers, there would be no room in our body for them. So that's why our body has to pick and choose what information is the most important, that needs to be transmitted the fastest, to have those large type A fibers, and other information that's not as vital, that it's immediate, can travel on those smaller fibers. So next up, in the next lecture, we're going to be talking about what happens at the synapse. So once that action potential reaches the synapse, reaches the axon terminal, the synaptic bulb, what's going to happen from there? So I had to include this Ryan Gosling "Hey Girl" meme because I just find it funny.